An electric dipole consists of two charges of equal magnitude and opposite sign separated by a distance 2a as shown on the next slide. The dipole is along the x-axis and is centered at the origin. If the electric potential is taken to be zero at infinity, calculate the electric potential at any point y on the y-axis. Calculate the electric potential at any point x on the x-axis in between the two charges. And if one charge q is 4 microcoulombs and a is 2 centimeters, how much work is required to bring a third point charge of minus 4 microcoulombs from infinity to the point at 1 centimeters on the x-axis? Now we have the expression for the electric field at a point on the x-axis between x equals 0 and x equals a. Let's now apply this to part C. Part C says if charge Q is equal to 4 microcoulombs, so that's 4 times 10 to the minus 6 coulombs, and if A is equal to 2 centimeters, which is 2 times 10 to the minus 2 meters, how much work is required to bring a third point charge of minus 4 microcoulombs from infinity to the point P, where P is the point x equals 1 centimeters, y equals 0 centimeters. Well, we know what the expression for electric potential is, but they're asking us to find how much work we would have to do to take a third charge and position it at a point on the x-axis. So in other words, if this were our x-axis, here's the origin, here's the location of the positive charge, here's the location of the negative charge. Positive charge is at A, negative charge is at minus A. We're at the point 1 centimeter. So 1 centimeter is equal to 1/2 A on the x-axis. And we want to take a charge from all the way out at infinity, and we want to figure out how much work is required to move the charge to the point x equals 1/2 A. Think about how you would do that. Well, remember, a change of electric potential energy is equal to minus the work done in moving a particle between 2 points. You should also remember that electric potential is defined as electric potential energy per unit charge. This means that a change of electric potential energy is equal to the charge times the change in electric potential. So the change in electric potential energy would be the electric potential energy that we end up with. This is going to be at the point, I'll label this point 2. This will be at the point 2 on the x-axis, minus the potential energy from when the two charges were separated by an infinite distance. And this is going to be equal to Q times the potential energy at point 2 minus the potential energy from when the two charges were infinitely separated. And this expression is just equal to minus the work done on the charge. Well, let's look at this. We defined, or we're using the convention that the electric potential energy at a point of separation infinitely far away is going to be 0. This means that the electric potential for two charges separated by an infinite distance will be equal to 0. This gives us that minus the work done is going to be equal to Q, that third charge that we brought in, times the electric potential at point 2. Well, this means that the work done is equal to Q, and the electric potential at point 2 is going to be our form that we got for the electric potential V evaluated at x equals 1/2 A. So this is then Q times, and I see I'm going to get into some notational challenges. So let's go back and relabel the charge that we're bringing in from infinity. Let's go ahead and label that as Q3. And that way we could keep the Q for our original dipole arrangement. So I just went back and relabeled that third charge Q3. So you'll remember from the previous slide that our formula for electric potential at a point on the x-axis is 2kq, x being our point on the x-axis. I'll call this x2, where x2 is equal to 1/2 A, divided by x squared minus A squared. So the work done is Q3 times 2kq over x squared minus A squared times 1/2 A. And I should put a 1/2 A here as well. I see that the 2 in the numerator cancels with the 2 in the denominator. So the work done ends up being K, Q, Q3, A over 1/2 A quantity squared minus A squared. This is just K, Q, Q3 over 1/4 A minus A, where I divided out an A in the numerator from an A squared in the denominator. For the work done, we now have minus 4k q q3 over 3a. So here's an expression for the work done in taking a charge that is infinitely far away and moving it to a point on the x-axis. Let's go ahead and substitute in the values we have. For the work done, we have minus 4 times the Coulomb constant, which is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared, times 4 microcoulombs, this is Q, times, I'm going to go to this next line, times a minus 4 microcoulombs, this is Q3, divided by 3 times 2 centimeters. Well, let's cancel some units. I see a coulomb squared in the numerator, cancels a coulomb squared in the denominator. I see a meter in the denominator, cancels with one of the meters in the numerator. I'm left with a unit of Newton meters, which is the same thing as a joule. So for the work done, we get 9.59 joules of work needs to be done in order to pull that negative charge from a point infinitely far away to a point at x equals 1 centimeter on the x-axis.